Hello everyone, and thank you for the opportunity to present today. I would like to discuss how to eliminate the Doppler aliasing artifact using a formula-based approaches. Aliasing is a signal processing artifact that occurs in pulse wave Doppler ultrasound when the Doppler shift frequency exceeds the Nyquist limit. And this is causing the waveform to be displayed incorrectly. The Nyquist limit is defined as the PRF divided by 2. When aliasing occurs, velocities that exceed the Nyquist limit appear to wrap around the spectral display, making high velocity flow appear inverted or falsely displayed on the opposite side of the zero baseline. Now this can lead to misconception of blood flow direction and the velocity, particularly in vascular sonography. Well, the next approach we're going to apply by simply increasing the PRF. That is, PRF and the scale function are the same. So increasing the scale function, that is, increasing the PRF, is going to basically increase the Nyquist limit. Why? Because the Nyquist limit is equal to half of the PRF. Then this is going to what? This is going to cause Nyquist limit to be greater than the Doppler shift, and this will eliminate an aliasing artifact. So I'm going to abbreviate as an AL, an aliasing artifact, or just aliasing, like that. Well, the third approach is going to be change in the frequency, decrease in the operating frequency. Let's go step by step. Why decreasing in operating frequency is going to eliminate the aliasing artifacts. So simply, let's recall the Doppler equation, where the Doppler shift is equal to 2 times operating frequency times velocity of red blood cell. And by the way, I'm annotating this as an actual velocity times cosine of the Doppler angle, theta d, divided by c. And according to this equation, the Doppler shift is directly proportional to the operating frequency. Obviously, decreasing the operating frequency is going to decrease the Doppler shift. Let's continue our statement here. So decreasing the operating frequency is going to... Now the fourth approach. That is going to be increase in the Doppler angle. So let's increase the Doppler angle. I'm talking about, physical increase in the Doppler angle. So we're going to recall the following, that Doppler angle and the cosine of the Doppler angle are in inverse relationship. So let's write that down right there. So they're basically increasing the Doppler angle. It is going to decrease the cosine of the Doppler angle. According to the equation above of the Doppler shift, what we can see that Doppler shift is directly proportional to the cosine of the Doppler angle. That is there. So it is definitely worth it to discuss point number 5. So we're going to decrease the depth. I'm going to annotate with the letter D, depth. And this would not relate to the knob that is present on our machine. We're going to find out a window where the depth is going to be physically decreased. So in other words, we're going to find another acoustic window which is going to be with a less depth to interrogate the structure. So decreasing the depth, let's see what happens and what is the equation that supports this. I'm going to go over the several steps here. And based on the range equation, we're going to define that the depth is equal to what? Depth is equal to C times PRP divided by 2. So simply recalling that the PRP and PRF are inversely proportional, I'm going to plug in the PRF value instead of PRP. So then, depth is equal to C divided by 2 times PRF. So I'm going to solve the equation for the PRF, and then PRF is going to be equal to C divided by 2 times depth. Half of the PRF is equal to Nyquist limit. That is. Let's continue. Let's create more space in here. I'm going to continue further. So dividing this equation by 2, PRF divided by 2 is going to be equal to the following. C divided by 4 times D. Now what we're going to do, we're going to equate the Nyquist limit with the Doppler shift. Frequency there. And then let's rearrange the equations, So C divided by 4 times D, that is equal to 2 times operating frequency times velocity of RBC. And again, I'm going to stress out the actual, not the measured one, times cosine of the Doppler angle divided by C. So then I'm going to solve this equation for the velocity of red blood cell. So basically now the velocity of RBC measured, it is equal to the following. C squared divided by 4 times 2, 8. Let's make it a little bit better. 8 times depth times operating frequency times velocity, times cosine of the theta d, Doppler angle. Now what is this equation about anyways? So this is the upper limit of the ability of our machine ultrasound units to measure velocity correctly, velocity ranges correctly. In other words, accurately measured velocity VRBC measured is inversely related to the depth. Decreasing depth is going to increase the PRF. Increasing the PRF is going to increase the Nyquist limit. Increasing the Nyquist limit is going to basically cause the Nyquist limit to be greater than Doppler shift. And this is going to eliminate the Aliasing artifact. There. And lastly, we should be able to switch to the continuous wave in case none of these choices helped. So switching to the continuous wave ultrasound is going to be eliminate completely the Aliasing artifact. Continuous wave Doppler study is immune to Aliasing artifact. With this, allow me to finish my presentation. And thank you very much for your attention, and I do appreciate your time.